All right, guys. We're back for some more ice tables. All right, so we left off in the last video talking about salts. Again, I'm gonna try to do a video hopefully in the next few days with more salt practice, because my guess is you're probably not 100% ionized. Just kidding. You're not 100% confident in that yet. But before I can do that, let's go ahead and finish up this chapter. So, the last two problems we will work are going to be with polyprotic acids. What is a polyprotic acid? A polyprotic acid just means it has more than one hydrogen ion. So when they ionize, it ionizes in a stepwise manner. That is, they lose one proton or hydrogen at a time. I was going to write hydrogen. That's H plus. Okay. So an ionization constant expression can be written for each ionization step. Consequently, two or more equilibrium constant expressions must often be used to calculate the concentration of species in the acid solution. So you can find the Ka table for your polyprotic acids in your textbook. It is table 16.10. I cut and pasted it on to into my notes so that y'all could see what I was talking about. But you can find this on page 721 in your text. So page 721, you'll find this table. All right, so you see here are, well, most of the time we'll be dealing with diprotic acids. Why did it do that? Then there are two triprotic acids listed here as well. The only thing I'll mention is you see for sulfuric acid, and we're going to work one with sulfuric acid, the first ionization is strong, so there is no Ka value because it goes to 100% complete, dissociates 100%. That's what I'm trying to say. So we use just the single arrow. The second step, it becomes a weak acid. The reason it becomes a weak, the reason it is a weak acid in the second ionization is because you already have hydrogens floating around in that solution now. And if you already have hydrogens, chances are that acid isn't going to want to give up any more of its protons, because when you took that first hydrogen, you made it negative. It doesn't want to be more negative. Okay, so it's always, any acid is always weaker in the second ionization, and then even more in the third ionization. Like you can see with phosphoric acid, the third ionization, the Ka, is 4.2 times 10 to the negative 13th. That is very small. Okay, so let's go down and let's do an example. So it says oxalic acid is a poisonous substance used chiefly as a bleaching and cleansing agent. We're probably using a lot of that right now. Calculate the concentration of all species present at equilibrium in a 0.1 molar solution. Okay. I've just scroll it down because I like to hover with my pen. All right, so this is what the first ionization will look like. I'm going to just take one hydrogen. These are my acidic hydrogens. So I'm going to leave oxalic the acid with one hydrogen. Okay, so we're told that it's 0.1 initially. So these are 0. And then we're going to do minus x plus x plus x. Bring all that down. Bet y'all are tired of ice tables. I know that I usually get tired of them about this time. And we skipped chapter 17 because that's even more ice tables. So be thankful. All right, I went ahead and I added in the Ka values here for this acid. I know it's not in your notes, but I added it here so that I didn't have to write it out. All right, so just as usual, we're going to plug in our equilibrium line in our Ka expression, and we're going to use the first Ka because this is the first ionization. So 0.06 x squared is going to be on top, and then 0.1 minus x on bottom. We cannot use the approximation because our initial concentration is fairly large and our Ka is not very small. All right, so let's go ahead and multiply both sides by 0.1 minus x. That cancels. And that's going to leave me over here. And distribute both of these terms. 0.1 times 0.06. Ooh. Get that, and then I'll just have 0.06x. Be careful with these zeros. Then x squared on the other side. All right, so then let's move everything to one side. So I'm going to move my 0.06 and my 0.06x to the other side. So I have x squared plus 0.0x and then minus 0.006. All right, so I got to go to the quadratic formula, plug these in. I'm not going to work that out, but just remember minus b squared minus 4ac all over 2a. Okay, so a is 1, b is 0.06, c is 0.006, well, negative 0.006. Okay, and the x values I got were 0.0531 and negative 0.113. So obviously I can't use this negative, so I'm going to use this positive. Okay, so that then I take the question asked us to find the concentration of all species present at equilibrium. All right, so I'm not going to plug that in just yet, okay? Crap, I need more room. Let's see what I want to do. No. I can insert a page. Cool. All right. Okay, so what I am going to do is I'm going to go ahead and write out my second ionization. So from the first ionization, 204, this is what I was left with. So now that is going to ionize again, giving off that last hydrogen. I'm going to be left with that. Okay, so how do I know my initial concentration of this species? Well, we solved for it in this problem. So when the first ionization is complete, we'll have 0.0531 hydrogen concentration and HC2O4 minus. Okay, so I plug this in down here. That's my initial concentration. Not only is that my initial concentration of this species, it is also the initial concentration of the hydrogen ion. We still don't have any of that. Okay, so since we have a reactant and a product present, normally we would calculate Q, but we don't have all product present. So our Q is still going to be telling you that the reaction is proceeding to the right. Okay, so I'm still going to subtract X here plus X plus X. So 0.0531 minus X, 0.0531 plus X, and then X. Okay, so now we do the same thing. We take our Ka, we plug this line into it. So the Ka2 is 6.1 times 10 to the negative fifth. Yes, let's try the approximation. Okay, so first off, this is what plugging that line in looks like. Okay, so we want to use the approximation. So we've done an example like this before where we approximated on the bottom and the top. We're going to do that here as well. So if I approximate and say that this X is not going to affect this concentration, so approximate it, I am also saying then that if I added it to that same number, it's not going to affect it. So I'm approximating there. Well, both of these numbers are the same, so I get 6.15 times 10 to the negative fifth be my X. Okay, we need to check the approximation. Make sure it's good. So our X value is 6.1 times 10 to the negative fifth over our initial concentration, which was 0.0531 times 100. And I got 0.11%. So it's good. We can use that approximation. All right, so the question asked us to calculate the concentration of all species present at equilibrium. All right, so that even means the original acid. 204. Let me clean some stuff up here. So I was talking to my mom earlier, and she was texting my little sister who's 11. She said that my sister told her that she was going to take a nap to pass the time because she was so bored. It's like, well, we've reached a new low. Ooh, I'd like to take a nap. Ooh. Okay, so from our first ice table, we had 0.1 as our initial concentration and minus X, and X was 0.0531. Okay, then we had hydrogen ion concentration and this concentration were equal at 0.0531 from your first ice table. Then we took it to the second ice table, and because we used the approximation, we said that adding X and subtracting X is not going to change this number. And you could actually do that if you want. It's not going to change that number. Then the last concentration we would add then would be this concentration. It was just our X from our second ionization. Okay, and this I didn't do here, 469. So this would be your final answer. So for polyprotic acids, you have to do as many ice tables as you have hydrogen ions. Okay, so let's do another one. The next example says find the pH of 0.01 sulfuric acid solution. All right, and you see I only wrote Ka2. That is because H2SO4 is strong in this first ionization, meaning it goes to completion. So if I start with 0.01, 0 this, I'm going to completely dissociate this into these two ions. That's 0, this is 0.01, 0.01. Okay, so now I can do my second ice table. Yeah, what's new? Right, so my second ice table would look like this. I'm losing the other hydrogen. Okay, well, my initial concentration of HSO4 minus is 0.01 from this step. My hydrogen concentration is also 0.01. And this is 0. So I do minus X plus X plus X. 0.01 minus X, 0.01 plus X. And then just okay, so now let's get our Ka2, which was 0.012 equals 0.01 plus X times X over 0.01 minus X. We cannot use the approximation here because our Ka2 is not very small. Okay, so great. All right, so I'm going to move this bottom part over. Then I need to distribute the top. So on the top, I distribute that X. It's going to be that. Right, I'll go down here and distribute this. Let's see, 0.012 times 0.01 gives me 1.2 times 10 to the negative fourth. Then 0.012 x okay. Why did it do that? Let me insert another page. What? Oh no, I wanted to insert it down here. Oh, the struggle. Here. Okay. Need to shift this up. Okay, there we go. All right, so let's move everything to one side. So I'm going to move everything on the left side to the right. So it'd be 0, 0 equals x squared. Then I'm going to do minus. What is all this? This should be plus. Right? No. Be minus. So I'm going to add this to both sides. So that's going to be 0.012 plus 0.01. I shouldn't have even had to do that. 0.022. And then minus. Sorry. 1.2 times 10 to the negative 4. All right, so again, my A is 1, B is 0.022, C is negative 1.2 times 10 to the negative 4th. Let's plug that into your quadratic formula. When you do that, I got x to be 0.0045 and negative 0.0265. Well, I don't want the negative. I want that. So the problem asked us to find the pH. So all I'm concerned with is the hydrogen concentration in this example. So my hydrogen concentration would be 0.01 plus 0.0045, which equals 0.0145. So now I'm going to get the pH from that. So negative log 0.0145. When you do that, I got the pH to be 1.84. Okay, so that's how you find the pH of a diprotic. All right, last thing. One more acid-base definition. So we've talked about Arrhenius acid bases and Bronsted-Lowry acid bases. The last definition is that of Lewis acids and bases. So this just broadens the range of our acids and bases. So the Bronsted-Lowry model focuses on the transfer of a proton. The Lewis model focuses on the donation of an electron pair. So what do I mean? So we have H plus we have NH3. If I drew out the Lewis structure of NH3, I would see that there's a lone pair on the nitrogen. So what happens is that lone pair bonds with this hydrogen ion and we form NH4. So we're focusing now with the Lewis acid bases on electron pairs. So the acid is going to be the electron pair acceptor. So it accepts the electron. It is an electron deficient chemical species. So it might have a plus sign. It might be a positive charged ion. Or it could be one of our elements that have an incomplete octet, like barium, beryllium, no, not barium, beryllium and boron. They only like 6 to 4 electrons. We call Lewis acids an electrophile, and if you're going on to organic, you will learn a lot about electrophiles. And I've kind of already mentioned this. Lewis acids are electron deficient species due to either being attached to an electronegative atom in a bond or a result of having an incomplete octet. Not having a complete octet, same thing. So atoms that are attracted to highly electronegative atoms or have multiple bonds can be Lewis acids. Again, you can add Lewis acids usually have a positive charge or an incomplete octet such as beryllium, boron, and aluminum. Lewis bases then are your electron pair donor. So in this example, NH3 was a base. It is an electron-rich chemical species, and we refer to them as a nucleophile. It's looking for a nucleus to join. A Lewis base must have a lone pair of electrons that it can donate. Anions are better Lewis bases than neutral atoms or molecules. So if it has a negative charge, it's a good base. And generally, the more electronegative an atom, the less willing it is to be a Lewis base because it doesn't want to share its electrons. The donated pair of electrons generally results in a covalent bond forming. So as an example, BF3 plus NH3. Boron has an incomplete octet, so it's going to be an acid. The ammonia has a lone pair, so it's going to be our base. And what it's going to do is it's going to form a bond between the boron and the nitrogen, just like that. This is called an adduct. An adduct is the direct product of two or more distinct molecules resulting in a single reaction product containing all atoms of all components. So an adduct just means I took two compounds and I put a bond in between them. Everybody came with. Like, we didn't lose any elements along the way. That's what an adduct is. Arrhenius, Bronsted-Lowry acid-base reactions are also Lewis acid-base reactions. Lewis just extends the definition of what an acid can be. Okay, so let's look at this example and we'll be done. All right, so identify the Lewis acid and Lewis base in the following reactions. A. Well, without even drawing this first species out, I look here and I see aluminum. That immediately tells me that it's a Lewis acid that has an incomplete octet. If I did draw this species out, I would see that there are two lone pairs on that center oxygen. so therefore it's a Lewis base. Here is the adduct that they formed. B is easier to identify because we have positive and negative charges. So if it's a positive charge, it has to be a Lewis acid. If it's negative, it's a Lewis base. And again, there's our adduct that we formed. If you would like more practice on those, number 122 and 124 on page 734 of your book. Do y'all have the answers to the evens or the odds? If it's the odds, just do the odd numbers that are right around here and check it in the back of the book. All right, we are done with acids and bases. Again, I'll try to get a another video of more salt problems in the coming days. So until then, bye.